think we'll go ahead and get started. Okay. First thing we're going to talk about is probability. We deal with probability quite a bit. It oftentimes gets mistaken with percent because percent is one way to represent probability. Maybe you might hear that there's a 80% chance that it's going to rain. Now, as we go through this course, if you need to find a probability for a particular problem, they give you the percent, they're giving you the probability. In decimal form, that would be 0.80 or 0.8. Now, if we looked at an example, and I'll use a card example. We got a standard deck of cards, 52 cards, excluding jokers. And I want to look at the probability of pulling one card out and getting a heart. Well, for our basic probability, we put our total number of possibilities on the bottom. So it's 52 cards, so I put 52 on the bottom. And what we're studying, in this case hearts, is what goes up on top. So out of those 52 cards, 13 of them are hearts. So that would give us 13 over 52. Then we could simplify that fraction, or you could put it in decimal form, and that would give us our answer. Maybe I'm looking at the probability of pulling out a king. So I'm picking one card out of random. That random part is true in every example I'm going to give you, probably in this course, but definitely on everything today. If it's not random, then you can't really say the probability. I mean, if I have the set up such that you're going to pull a king out, then the probability you're going to pull out a king is 100%, or 1. Okay, so it's 52 cards. And what I'm studying goes up on top. So I'm studying kings, so I'd have there's 4 kings in a standard deck of cards. Now, sometimes we have to, and I think one of the problems asks you to build a probability distribution. For example, if I looked at hearts, spades, diamonds, and clubs. And I'm taking a look at getting the probability. This is based upon one card being pulled out of a standard deck of cards. Probability it's going to be a heart is 13 out of 52. We already saw that. Probability it's going to be a spade is 13 out of 52. Diamonds will be 13 out of 52. And clubs will be 13 out of 52. You can see by looking at these fractions right here that each one of these is equally likely. So if I pull a card out, I got equal chance of being a heart, spade, diamond, or club. Now, that's if you build your own probability distribution. Sometimes you're given a frequency. For example, maybe if I look at colors, I got red, blue, and green. Then if I'm given frequency, let's say there's 21 red ones. There's 2 blue, and there's 13 green. If you're asked to come up with a probability distribution, probability model, what you have to do is you add these together. That's 23, 26, 36. 36. And then our probability, which you can think of it as the same as relative frequency, we take each one of these frequencies, divide by our total. So I got 21 divided by 36. I got 2 divided by 36, and I got 13 divided by 36. And I won't actually plug those in, but whatever that gives you would be your probability. Nice part about Excel is that'll do it for you real fast. Let me show that. Okay, so let's see, I got the colors here. Red, blue, green. And I got my frequency. 21, 2, and 13. Well, I need to sum these up. So I'm going to click my auto sum here. Remember the uppercase sigma. And that'll give me the formula equals sum B2 to B4. B2 is my first cell, B4 is my last cell. And I'll do the check mark here to go ahead and accept that. Okay, so now our probability, we're going to take equals 21. Now, I should say what I did there. I did an equals, and then you could type in B2. You could use your arrow keys, divided by B5. Okay. So you can see that's dividing this by this. Now, probability is usually written in decimal form. If you want it in percent form, you need to multiply by 100. Now I'm going to fill this down, and let's see what happens. I get a couple of errors. Okay. Let's go back to this. This is called relative referencing. I remember the correct term, in Excel. And this is where, as you fill down the formula, if this is B2, then the next formula here will be B3. The next one will have B4. So it automatically adjusts it as you fill it down, trying to anticipate what your formula should be for those other cells. Now B5, and then down here it says B6, and then B7. But we want it always to point to B5. Now, how we can specify, that's called absolute referencing, is you put dollar signs in front of the B and in front of the 5. There's a very clever way to do that, but that's a very easy way, is just put dollar signs there, and then press enter. Doesn't change my first one at all, but now if I fill down, you'll see these other two are okay now. And you see if I click this, it says B3, B5. If I click this one, it also says, did I say B3? B5. Let me do that again. My eyes really aren't that bad. So B5. So that's how you can handle relative referencing versus absolute referencing. If you want it always to be a certain cell, then that's absolute referencing is where you want to go. You can use name cells too, but we're not going to get into that in this course. Okay, so that's how to build a probability distribution. Now for a probability distribution, all these probabilities have to be between 0 and 1, which they are, and they have to add up to 1. I'm not sure if they'll add up to 1 here. You might have some rounding issues, but if I click auto sum and then choose this check mark or enter, it does give us 1. So that's a probability distribution. Okay, sometimes you're given tables. Like maybe education here of high school, college. Over here on the side, I'll have hair color. Blonde, let's see, black hair, brunette. And 20 here, 10, 5, 23, 17. Whatever these might represent. So, if I look at this cell right here, this would represent for high school students, how many of them have blonde hair. This would represent for college students, how many of them have blonde hair. Black hair, how many high school students, how many college students, and so forth. Now, when you're figuring probabilities with a table, it's usually best if you go ahead and put your totals in there, if they're not already in the table. So if I do total here, I'm just going to choose this auto sum, uppercase sigma, check mark, and I'm going to fill that over. I'm not sure if let me try to fill it over there. I'll do auto sum here, and then I'll fill it down. Now this number that's in the very bottom corner here, this is going to be our grand total. That's how many we have total. So now, if I were to answer a question on that data, I'm looking at the probability of picking one person out and getting a high school student with brunette hair. With brunette. I probably spelled that wrong. Too bad there isn't a spell check on this tablet. I'll abbreviate it. There we go. Okay, so the grand total goes on the bottom. Well, that'll be what's in this bottom right-hand corner, 75. Now I'm looking high school students with brunette hair. High school with brunette hair is this cell right here. That'd be 3. So that'd give us our answer. Now maybe they're asking you what's the probability that you pick one person out and you get a high school student. Well, 75 goes on the bottom. That's our grand total here. And we have to look at the column total for high school. That adds up to 28. So 28 goes on top. So again, if you have those totals, it really does help with your problems. If I'm given markers, I won't write out markers, but I got 2 blue, 3 green, and 1 red. Well, right away, before I'd even work a problem, I'd count them. I got a total of 6. So 6 total. Okay, so then I pick a marker out at random, and I'm looking at the probability that it's going to be blue. Well, since we already have our total, we know 6 goes on the bottom, and what we're studying goes up on top, which would be blue. Now that's our very basic probability. I'm not going to go into these in a whole lot of depth. There's YouTube videos I put out there that cover these. I'm just kind of giving you a general introduction here. Now these are more than just fractions. If I came out with 1/2 or 0.5, 50%, however you want to write it. This would say that a probability of something occurring is 50%, assuming that I look long term. These are not geared toward short term. I could flip a coin and get heads 3 times in a row. That does not mean I'm going to get heads every time, unless I have heads on both sides. So what this says for probability is that long term, we expect that half of them will be heads, half of them will be tails, because there's 2 possibilities. Okay. Now you might have some problems dealing with an or. I pull a card out of a deck, and I'm looking at the probability that it's going to be a king or a queen. The or is our addition rule. That means we're adding. So we're going to have one fraction here plus another fraction here. Well, there's 52 cards. Of those 52 cards, 4 of them are kings. So that'll be 4 on top. Over here, there's 52 cards. Of those 52 cards, 4 of them are queens. So that'd give us 8 out of 52. And that would be our answer. Now, in some cases, you don't have to derive this fraction yourself. They give it to you. When I say they give it to you, they may not give you the exact fraction. They'll give you a percent. They'll say that the probability that you're going to pick out a king on a single card being drawn out of the deck is equal to this. So they already give you the probability or percent. Now, compare that to pull a card out. It's going to be a heart or it'll be a king. So we got 52 cards, 13 of them are hearts. Or is always addition. Then we got 52 cards, 4 of them are kings. Now there's a problem with what we have come up with here. Is we're looking at this can be a heart or a king. Well, here we counted the king of hearts. And here we counted the king of hearts. So we counted the king of hearts twice. So we had to subtract off 1 out of 52. So sometimes you have to do an adjustment if you count more than once. Now, this talks about whether these have any shared outcomes. For example, this is a heart, this is a king, And this right here is probability that's a king and a heart. And so that's why we counted the ones that are king and hearts as 1 out of 52. Over here, they didn't have anything shared. This is a king, this is a queen. They can't be a king and queen at the same time. Now that's the OR. Let's talk about multiplication. Okay, so we're pulling a card out. The first card is a king. And the second card, this is a first card. And our second card is a queen. Now on these problems, you have to figure out whether replacement applies or not. Usually it will say if it's meant to be replacement. It might say, okay, pull one card out of a deck and then replace it, put the card back in, and then pull another card out. Now I'm going to assume no replacement here. So when it's all said and done, you should have 2 cards in your hand. Well, if we look at our first card, we said it's going to be a king. So it's 52 cards, and 13 of them are kings. Let's try that again. 4 of them are kings. Now I visualize this. I visualize a specific example. That specific example is not actually part of the problem, but it helps me to think about the setup. Let's say I pulled out the King of Hearts. So I have the King of Hearts sitting here over on the side. Now the AND is always multiplication. So then the Queen, is there 52 cards left? No, we pulled that one aside, so there's 51 cards, of which 4 of them are queens. Now I pull out Queen of Hearts. Of course, there's no other conditions here, but this would give us our probability. Now let's say you're going to pull out 4 cards, and you're looking at the probability that they're all kings. And there's randomness that fits into this and everything, so I'm not going into that. Now here, there's no AND here, but there's an implied AND. We're saying the first card's a king, and second card's a king, and third card's a king, and fourth card's a king. So even though there was no AND specifically there, it's implied. Okay, I'm visualizing this. Now I got 52 cards. 4 of them are kings. I pull out the King of Hearts, for example. I've now set the King of Hearts to the side. So how many cards are left in the deck? There's 51. Of those 51, there's 3 queens still left in the deck, because I already took that one king, and I say queen, 3 kings still in the deck, because I already took that one king, took it out, and set it aside. So there's 3 kings left. Get more sleep at night. Now our next card, let's say I pulled out the King of Diamonds. I can draw a diamond very well. So now I got the King of Hearts and King of Diamonds sitting over here on the side. I got 50 cards left, of which 2 of them are kings. Now let's say I pull out the King of Clubs. So now over here on the side, I got the King of Hearts, King of Diamonds, King of Clubs sitting there. There's 49 cards left, of which there's 1 king left in the deck. So that would give us our probability. Now sometimes on these, you have to think of possibilities, sample space. And the book talks about that, and the videos talk about it some too. So that comes in. If I'm going to roll two pairs of dice, and I'm going to get the probability that the sum is 10. Now sometimes you could possibly use ORs and ANDs for these, but sometimes you can just think through the sample space. So sum is 10. Well, what gives us 10? Well, 5 and 5 does. 4 and 6, but also 6 and 4. Now you might say, well, those are the same item. Why are you putting them down twice? Well, this says I'm going to get 4 on the first die, and this will get 6 on the second die. This one says I'll get 6 on the first die and 4 on the second die. Now you might say, well, why don't you flip these around? Well, I don't flip those around because they're the same number. You get 5 on the first die and 5 on the second die. That's the same as saying you get 5 on the first die and 5 on the second die. So there's those possibilities. Now we got 3 and 7, and 7 and 3. But what's wrong with these? Well, think of what's possible. With a die, you have 1 through 6. You don't have 7. So sometimes you have to have a little bit of knowledge of whatever you're dealing with to really understand how the setup should go. If you're not familiar with how many cards are in a deck, how many hearts there are, if you're not familiar with dice, well, then you'll list some other possibilities that don't apply. Okay, so here we're going to have 36 possibilities. There's 6 faces on each die. So a multiplication rule, which you'll read about, says the total number of possibilities will be 6 times 6. That's always true when you're rolling a pair of dice. And the number that add up to 10 looks like 3. So that'd give us our probability. Clear that off. Now, I will tell you this basic probability is probably what a lot of people find the most challenging part of statistics. So don't get frustrated with this. As you're sitting there working the problems, it's like, boy, this just seems there's no pattern to them. You're going to find as we go on, there's patterns in all the other sections, more or less. So it's not as frustrating as this material here. A lot of times when people see me work it, they say, well, that seems pretty simple. But then when they start to all mixed in, you're trying to figure out, is it multiplication, is it addition? It becomes a challenge. Remember when I took statistics way back when, it seemed like in a basic probability portion, it seemed like every problem was different. One time the wind was blowing, next time the wind wasn't blowing. And I couldn't understand how there could be so many different variations, I guess. Now that I teach it, I don't have any problem with it. Okay. Now, let's go back to our example here. And I'm going to look at the probability of getting a high school student given they have blonde hair. When you see this vertical bar in probability notation, this means given. The given means I'm narrowing this down. I'm not looking at the total amount down here at the bottom, but I'm looking at the total number of blonde. Well, if I go over to blonde, the total number is right here, is 30. Now, given I'm only looking at the blonde right here, then we have to ask ourselves, of that 30, how many of them are high school students? Well, 20 of them. So put 20 up on top. And that'd give us our probability. Now, sometimes it's flipped around. We're looking at probability of blonde given a high school student. Now, whatever follows your given here is always what goes in the denominator, the bottom. So high school students, if I see I got 28 high school students, 28 goes here. So again, that dictates what goes on the bottom. This dictates what goes up on top. Now, it's not the total number of blondes. It's given I'm only looking at the high school students, which is this right here. Given that I'm only looking at the high school students, how many of them are blonde? Well, of these, I see there's 20 blonde. So that'd give us 20 out of 28. So again, here the blonde is what dictated the bottom number, and of the number of blonde individuals, we counted how many are high school students goes up on top. Now that's the conditional probability where you have a given. Clear that off. Maybe. There it goes. Let's say I'm got a test, multiple choice test, 20 questions. There's 4 parts to each problem, one of which is right. And I'm guessing. And I'm looking at the probability that I'm at least going to get one right. Maybe I need to get at least one right to pass the course. Now, some wording here. Whenever you see the wording at least one, now this applies for basic probability. It doesn't apply when we get into distributions. Distributions are handled differently. But whenever you see this with basic probability, this is our at least one rule. So we're going to rewrite this as 1 minus probability of at least one right means none right. Now at this point in time, the wording here, right matches. So that stays exactly the same. All we did is replace this as 1 minus probability of none. And let me bring up the formula here. That might help. Assuming I can remember which section it's in. This is from a different book, so don't be looking at 5.4 in yours or 5.3. Computer's a little bit slow. Okay. Try this one. I want you to see that there is a step-by-step approach I'm taking on this. That it's just not random. Here it is. Okay. Now this is the idea. Whenever it says at least one something out of n, then you rewrite it as 1 minus probability of none something. Well, that's what we did here, where the wording matches, and this always says none. Always says none in these. Then we're going to rewrite it as 1 minus probability of all, and then we change right to the opposite of right, which is wrong. So at this point in time, this here changed the opposite meaning, and we rewrote none as all. And it's always that way. You always rewrite as 1 minus probability of all. So then we look at a single event happening and look at probability it's going to be wrong. There's 4 parts to each, 4 multiple choice parts, A, B, C, and D, one of which is right. So if you're guessing there's 4 parts, and probability it's wrong will be 3 out of 4. Because if one of them is right, then 3 of them are wrong. And then we put the power on here. There's 20 questions, so we put 20 there. And you can plug that in your calculator, and that would give you, or in Excel, that would give you the probability. Now let me talk briefly about how to put that in Excel. I don't remember if I showed this last time. Equals 1 minus 3/4. I'll do the parentheses. Caret is how you do a power. So caret 20, and then press enter. And that gives us our probability there. Now that's our basic probability. And we'll be referring to probability throughout a lot of this course. Probability is very important. It allows us to do predictions. If you're coming out with a new drug, your pharmaceutical company, you come out with a new drug to lower cholesterol. Well, you can use the results of a sample to predict the success. So you're trying to predict the future. You obviously don't want to release a drug that's going to cause a lot of lawsuits. You see that on TV all the time. Where they got a big one they got out now is hernia repair. I see on TV. It's calling you, asking you to call in if you've had any kind of issues, so they can sue the manufacturer of the that particular product. So you're trying to avoid those. So that's where you do your samples, you do your studies, to then use that to predict. Is it working? Are you going to have troubles? And so forth. Elections. Polling. They do polling. Again, the idea there is to predict. a lot of statistics is predicting the future. That sounds strange, but more of a scientific way of predicting the future. Back when I was single, I dated a woman one time. She was late to dinner. I don't remember if it was our first date or second date. It was our last date. I remember that. But she came to dinner and she said she was sorry she was late. She had just come from mass, and I looked at her kind of weird, and I said, "Well, mass? Well, what do you mean?" She said, "Mass, the Catholic." So I said, "Okay." I said, "I thought you said you were Buddhist." And she said, "Well, I am, but I want to cover myself, make sure I don't go down to the hot place just in case the Buddhist part is wrong." But then later in the evening, she talked about how she went to see her fortune teller earlier that week, and she's going to be having a baby soon. Well, that puts a damper on any first or second date. So you shake hands at that point, and you wish them well. She was using, and no offense if you're into fortune tellers and so forth, but she was using a non-scientific method to predict future. Well, obviously in business and education and psychology, medical, you want to use sound methods to predict future. You still might be wrong if you look at the last election. They were really wrong on their surveys, their polls, and their predictions. But at least it was done in a scientific manner. Now, if it's done correctly, you'll have a higher chance of success with your predictions. There was a new place opened up in town here, barbecue place, and pretty good at place actually. I told him I was shocked that he was receiving so much business. Typically, a small town I'm in is not very supportive of new businesses. I said I was happy about that because his food's pretty good, but he was already talking about expanding. Again, he wasn't using scientific methods, but he was looking at, hey, I got pretty good success, and I want to expand out since obviously it's going to continue, and so he was using that to kind of predict the future. Okay, so let me close some of these. That's my little spiel on basic probability. Let's talk about permutations and combinations. This gets into the section dealing with how many possibilities you have. You count something. This kind of goes hand in hand sometimes with sample spaces. One time this was back before I had air conditioning. Not just last time. Air conditioning broke recently, but this is some 22 years ago when I didn't have air conditioning all in my house. I was trying to fix my computer. I wasn't fixing it. I was upgrading it. I was putting a new hard drive in there. And I already had one in there, and I wanted to add a second one. Well, it used to be that you had little pieces of wire coming out here. Dip switches, I think is what they're referred to. I need to learn those. Like that. And you put a piece of plastic over these that had a metal connector in there that would make the connection. And you had one as primary and one as secondary, so you had wires coming out to these. Then you daisy chained them off like that. Well, I put my wires in there, and I put the settings on there, and it didn't work. I thought, okay, that's strange. So I sat down there then and put them elsewhere. Didn't work. I must have tried, I don't know how many times I tried, but I think about 2 a.m. It was hot. I was sweating. I decided at that point I'm just going to buy a new computer. I couldn't get either hard drive to work at that point. Woke up the next day and I started thinking about it. I started thinking about sample space. Well, if I label these, this is A, B, C, D, E, F. Possibilities I could have A and D, little plastic on both those. I could have A and E. I could have A and F. I could have B and D. I could have B and E. I could have B and F. I could have C and D, C and E, and I could have C and F. So there's 3, 6, 9 possibilities. So 9 possibilities. I sat there and I tried each one of them. So I put it on A, I put it on D. Didn't work, I crossed it off. Then I put it on A and I put it on E. Tried that. Didn't work, I crossed it off. And so on. And I don't remember which possibility it was at this point, but once I got down to the correct combination, both hard drives worked. So this showed that just coming up with sample space can help you in some cases. Helps you to logically think through instead of thinking I'll just buy a new computer. What can you do? Well, there's 9 possibilities here, and we're going to take a look in this section. How do you figure out how many possibilities can you have? Well, we can have 3 possibilities over here. So we got 3. We can have 3 possibilities over here. So 3 times 3 is going to give us 9 total possibilities. This is the multiplication rule. Now, if I had another piece of PC equipment that had more dip switches, I think that's what they're called. Let's say I had 20 over here, and I had 40 over here. Well, my total number of possibilities would be 20 times 40, probably be 800. Well, this might be a little bit too excessive to sit there and write those all down on a piece of paper and try all the possibilities. So this is where I might want to go into the documentation. Didn't have access to internet back then, but nowadays access the internet and see what these switches should be. Okay, so now that we talked about that, number of possibilities. The book will describe permutations, combinations. My video does. So I'm really just going to take a look at how do you calculate it. Let's say I got 20 people, and I got a combination. NCR. C refers to combination, N refers to how many of them have, and R is how many I'm going to pick. So out of 20 people, I'm going to pick 5. Well, I could pick the first 5 people. I could pick the first 4, and then the next, skip that 5th person and pick the 6th person. How many different possibilities are there? Well, in Excel, combination is N, R. COMBIN. So if I come over here, I do equals combin, and then do a beginning parentheses, and our number is 20, and the number chose is 5. This tells us there's 15,504 different possibilities. Probably don't want to write all those down on a piece of paper. It's a little bit too much. Now for our permutation. We got 10 people, let's say, and P represents permutation. N is how many we have, and R is how many we're picking. And I'm picking 2 people out. So out of 10, pick 2. And this is permutation is what it's short for. And I put in 10, 2. And that gives us a total of 90. Now the hard part on this is when you talk about combinations and permutations to think whether order matters or not. If you got a permutation, this is where order matters. And if you got a combination, this is where order does not matter. It's hot here today, and I was proud of my son. He went out and he wanted to work. Didn't even ask for any money yet. I'm going to give him some, but he went out there and he worked for a couple hours out in the heat. And let's say I was going to pick, and he cleaned my truck. Let's say I was going to pick 2 people to clean my truck. Maybe I got a class. I don't have 20 children, but maybe I got a class of 20 people. I'm going to pick 2 people to go out and clean my truck. Well, whether you pick first or second doesn't matter. You're still just cleaning the truck. So in that case, order does not matter. Now, if I said I'm going to pick 2 people and the first person gets to do the fun part of cleaning, that they actually get to drive the truck down to the car wash and do the little nozzle, and that's kind of the fun part. And the other person has to use the Fantastic and paper towels to kind of clean up the floor and the grease spots and so forth. Well, then order would matter, because whether you pick first or second, definitely it would be different positions. One you're the water cleaner down there at the car wash, and the other one you're cleaning the grease and grime. When you're looking at these problems, you have to think about whether order matters or not. And again, that's the challenging part. Okay, that's our permutation and combination. So let me close that. Now, binomial probability distribution. I'm going to talk about the definition here, even though it's talked about in the video, because it really is important for you to understand the problem. Now, definition. Procedure has a fixed number of trials. Trials must be independent. Each trial must have all outcomes classified in two categories. Probabilities must remain constant for each trial. I went and ate, I got tacos from Taco Bell last night for my son and me. My wife was up with her brother and taking care of him. And so I was being a bachelor last night. And I didn't want to cook, even though I had air conditioning back. I didn't want to cook, so I went and got some tacos from Taco Bell. Let me bring up something here. Okay. Let's talk about if I were to ask you how many tacos. I ask 20 people. I ask them how many tacos do they eat each week. Of course, I'm talking about an average here, so I know people eat different amounts each week. A lot of them maybe zero. Procedure has a fixed number of trials. Yeah, talk to 20 people. So that's a fixed number. Trials must be independent. We assume that's true in a lot of these cases. Where it wouldn't be independent would be like if I'm picking cards out of a deck. I'm picking 5 cards out. Each card I pick out affects the probability of the ones that come after it. And we saw that with the probability. Each trial must have all outcomes classified into 2 categories. How many tacos? Think of what your answers are. 1, 3, 5, 0, 20, 30. That's not 2 possibilities, is it? So this would not be a binomial. On the other hand, if I talk to 20 people and ask them, do or did you eat tacos last week? Now this is different. I was going to put, do you eat tacos every week? Well, it's probably an unusual person to eat tacos every week. 20 people. Procedure has a fixed number of trials. That's true. And trials must be independent. We assume that's true. Each trial must have all outcomes classified in 2 categories. Either you ate tacos or you didn't eat tacos. Now, I was looking at some of the problems in the online homework system for this. Applia, or however you pronounce it. I don't even remember the name of it, to be honest. And I was working some of them myself. And you had to decide whether you're dealing with a binomial distribution or Poisson distribution. And when I was looking at these, really the main thing I thought of is there are 2 possibilities. Is it, did you eat tacos or not eat tacos? Do you believe in reincarnation or not believe in reincarnation? I can't even think of the example I was seeing on the homework system there. But again, using that basic idea of a yes or no type question being binomial helped me to figure out which one to use. Because Poisson is not a binomial distribution. It's not a yes or no type of question. Let me grab a drink here. Okay. Now, little p is probability of success in one trial, and q, or 1 minus p, is probability of failure in one trial. Success and failure has no connotation in terms of good or bad. Success is whatever I'm studying. Success might be that a bird gets hit by a truck on the road. Well, that's not a good thing. Well, depends if you hate birds, maybe. So what I'm doing with a success is just whatever I'm studying. So failure would be that they don't get hit by a truck on the road. So they either get hit or they don't get hit. So 2 possibilities again. N is number of trials, X is number of successes in N trials. So I'm studying 50 birds that live near the road, and I'm studying the probability that 20 of them get hit by trucks in like a month's time or something. Okay, now some of this is by tables, and we're not going to show that. You can watch a YouTube video and I cover that. This is how we're going to do it in Excel, though. Finding probabilities. Identify the number of trials, N. Identify the probability of a single trial, little p. This is often given as a percentage. List the x values the problem entails and rewrite with inequality/equality symbols. Step 4, use a table in the following slide to determine how to enter the function, and that'll give us our probability. Now here's our table, and I'm going to come back to this. It won't mean much for me to simply read that off to you, but the forms will. This is where it's exactly equal to one value. This is where it's less than or equal to one value. This is when it's greater than or equal to one value, and this is when it's between two values, including those two values. Okay, so let's look at some examples. We got probability of exactly 8. Up above, they tell us n is 30 and p is 0.25, and it's binomial distribution. So n is 30, p is 0.25. Okay, identify number of trials n and p, which are both given, so I don't need to worry about that. List the x value the problem entails. Exactly 8. That means x is equal to 8. And rewrite with inequality or equality symbols. This is already written with an equals. Now we want to look at our table. The form it's in is this one right here. Probability x is equal to a. So 8 is going to be our a. Now from our formula, we're going to have that's equal binom dist, beginning parentheses, a n p, false, a, which is 8, comma, n, which is 30, comma, p, which is 0.25, and then false. So let's go put that in Excel. Let me clear those out. Okay. Equals binom dot dist, beginning parentheses, 8, comma, 30, comma, 0.25, comma, false. And that'll give us our answer. Now B. What is B? B is less than 17. Now N and P is still the same, so I don't need to do that. I jumped directly down to listing the x values. Well, what does that mean? Less than 17. That means x is equal to 0, 1, 2, all the way up to less than 17 means it does not include 17. So that'd be 16. This is what's called a discrete distribution, means you have no decimals. Now we want to rewrite that with inequality symbols. 0 to 16 would be the probability that x is less than or equal to 16. Well, if we go to look at our table then, here's the less than or equal to case. So 16 is going to be our a. And this formula says we're going to do equals binom dist a n p, so a, which is 16, n, which is 30, p, which is 0.25, and I think it's true. Okay, true. Okay, so let's go put that in Excel. Equals binom dist 16, comma 30, comma 0.25, comma true. And that gives us our answer. Now C. C says at most 12. When you have to write down the x values, that includes 0, 1, and that includes 12. Now, I had students the other day in statistics who were having trouble with the wording. So, well, how can you tell whether that includes 12 or not? I said, think of it as if you're giving somebody money. I'm going to give you at most $12. Well, I could give you $0, $1, $2. At most 12 means I could give you $12, but I'm not going to give you over 12. So it's from 0 to 12. Now, to rewrite this with inequality, this goes from 0 up to 12, so this is x is less than or equal to 12. So this is the same setup as the one we just looked at. The number here would be our a. And we go look in our table. Probability x is less than or equal to a says we're going to set it up this way. So we're going to do binom dist, a in p, and then true. A is 12, n is 30, p is 0.25, and then true. And that'll give us our answer. I won't actually plug that into the Excel. I think you saw that with this one. Let's look at D. More than 20. Well, let's write down what x values that means. More than 20. That doesn't include 20. It means 21, 22. And since our largest value we can have is 30, that'll be from 21 up to 30. Now, if I rewrite this with inequalities, this is the probability that x is going to be greater than or equal to 21. These were the less than case. This is the equals case. These were the less than case. This is the greater than case. Greater than or equal specifically. Now from our table, greater than or equal to, that's this one right here. You see, you do not want to set it up with like a greater than and less than. You want to set it up in one of these forms, and all of these have the equals on them. Okay, so probability x is greater than or equal to a. That means 21 is our a. And we want to plug it into this formula here. Equals 1 minus binom dist, a n p true. A was 21. N is 30. 0.25 and true. Okay, so we got, what one is this? D equals 1 minus binom dist 21, 30, 0.25, and then true. And this is, realize this is not your probability. A lot of people have trouble interpreting the results on this. This is 3.758. E negative 08 or minus, or I forget what it is. But what this means is this is scientific notation. This means you're going to move your decimal point 8 places to the left. So that'll be point 1, 2, 3, 4, 5, 6, 7, and then one of the decimal places is a 3. 758. Your probability has to be between 0 and 1. So you can't have probability of 3.8, for example. So something to keep in mind when you're working problems. Can't have negative probability. Now it won't work E, because that's another greater than or equal to. But let's look at F. Probability between 10 and 20 inclusive. Means it includes 10 and 20. Well, let's write down what x values that entails. So it's 10, 11, all the way up to 20. Now to write it with inequalities matching one of these forms, this is going to be between two values, this last form. So we're going to have probability that 10 is less than or equal to x is less than or equal to 20. Now from our formula over here, a and b, this would be a and this would be b. And then we're going to plug it into this binom dist. After you've done the setup and identified your a and b and which type it is, it's just plugging in your values. B was 20, N which is 30, P which was what, 0.25, comma, true, close parentheses, minus binom distribution, and what's this one here? A minus 1. A was 10, so this will be 10 minus 1, comma, N, which is 30, comma, 0.25, comma, true. So that's how I'd plug that in the calculator. What is this? This is F. Equals binom distribution 20, 30, 0.25 true minus binom dot dist 10 minus 1. You could put in 9 if you wanted to. 30, 0.25 and true. And that'd give you your answer. So again, this table, a lot of people struggle with binomials. Like, how in the world did I do it? Well, your goal is to rewrite it in one of these forms, and if you do, then you just simply plug in your values at that point. Makes it a lot easier. Now, just one last item. If it asks you to find the mean is m times p. Asks you to find the standard deviation, sigma. That's the square root of n times p times 1 minus p. So again, n and p is all you need for that. N is like how many you're talking about, if we're talking about 30 or whatever. And little p is what's probability of one event occurring. You know, like if you look at one individual type of deal. Okay, that's binomial. Let's take a look at Poisson distribution. And I think that stands for fish. It's been a long time since I've had French, but I think that was stood for fish. But that's not who it's named after. The person's name is Poisson. This is a discrete probability that applies to occurrences of some event over a specified interval. This would be where I have an even amount of people coming into McDonald's from 11 to 12. And I'm looking at what's the probability that I'm going to get more than 15 customers type of deal. It's not a yes or no. It's more based upon numbers. Here's a formula. Don't worry about that. What I really want to focus on down here is the mean. Mean is lambda times t, and the standard deviation, sigma, is equal to square root of mu, which is the mean. It's like, well, what does that mean? Well, we'll talk more about that. To find the mean, you have to take your lambda times t, so it'd be 5 times 10, so my mu would be 50. And then I could plug in the values in to find the standard deviation. I'm not going to show that. Okay. Here's the part I want to focus on, finding probabilities. Identify the average number of occurrences of the event in some interval. Lambda is that weird symbol is lambda, and number of intervals is t. You want to calculate the mean, and that's usually lambda times t, although there might be variations of that. List the x value the problem entails and rewrite with inequality/equality symbols, and then use a table on the following slide to determine how to enter the function. This is pretty much the exact same idea as a binomial. you try to get into one of these forms, either an equals, less than or equal to a value, greater than or equal to a value, or between two values, and then you'll plug it into one of these. Okay, so let's take a look at these examples here. Let me clear this off. Okay. So my first one is probability of exactly 8. Well, that's x is equal to 8, so that's exactly one value. Lambda's t is equal to 5. So our mean is going to equal to lambda times t, which is 2 times 5, or 10. Okay, so this is already written in the form of x equals. So if I come over here, that's this one right here. So the 8 would be our a. And this tells us we need to plug it into equals Poisson.dist, beginning parentheses, then we put our mean in, which we said was 10, comma, a we said was 8, and then false. I won't actually plug all these in to the calculator. I think you get an idea on that. But here I do equals Poisson dist 10, comma 8, comma cumulative. False. And that gives us our answer. Okay, let's look at a less than or equal to case. This says probability that it's less than 17. Well, let's write down what x values that means. So that's going to start at 0. 1, 2, less than 17 means it will not include 17, so it'll go up to 16. Now we want to rewrite this as an inequality, so this is probability that x is less than or equal to 16. Now we don't want to do this. We don't want to do less than 17 because that isn't in my table. I don't have a less than. I have less than or equal to. So now it matches this one right here. So the a is going to be our 16. And this says we're going to plug it into equals Poisson distribution mu sub x, which is our 10, comma a, which is 16, comma, and then we'll put true here. True refers to whether it's cumulative or not. False, it means just a single value. And that'll give you your answer. I won't actually do that one. Let's go to a greater than or equal to case, like D. More than 20. Now, the thing about Poisson is we assume infinity, even though it doesn't make a whole lot of sense. So when you say more than 20, that means 21, 22, on forever. How many people can you go to McDonald's during a lunch? 500 people? Maybe. 1,000? Probably not, but maybe. 10,000? Wichita, I think, Wichita area has a population of about 500,000. Could you have 500,000 people converge on a restaurant during lunch hour? Yeah, you could. Be backed up quite a ways. I know they had that when they had those Beanie Babies, or I forget what it was exactly they were selling. It's just like there's a lot of people lined up. They had police would have the part of the road blocked off for all the traffic that was parked there. So again, even though infinity does make sense, we treat it as infinity. Now inequalities. 21 on up means probability that x is greater than or equal to 21, which matches our third form here. So a is going to be 21, That's our A. And what does this tell us to plug it in as? Equals 1 minus Poisson distribution. Mean, which is, what does it mean? 10. And then A minus 1. I don't remember if I did the A minus 1 in the binomial earlier. I had to bring that up just to make sure I told you correctly. So this would be 21 minus 1. And if you plug that in, that'd give you your answer. So, let me make sure I got the table correct on that. It wouldn't be good to give you an incorrect table. Ah. Let me think this through. Okay, if I said that I'm interested in probability x is greater than or equal to 20. That's 21, 22, or 20, 21, 22, and so on. So that's what that would be. This right here, 1 is everything. So that'd be 0, 1, all the way up, 20, 21, 22, so on, minus, and then binomial distribution, A, phone ring, but don't worry about it. So I got A. I'll let it finish reading. Well, this should be A minus 1. Because if I did A minus 1, then this is... Strange. I received text on my my regular phone. Okay. Now if this is A. Okay, so boy, that just is throwing me off thinking about that there. Okay. So if I subtract it off, that's 1. That's everything. If I subtract off from the A minus 1, it's up to 19. Then that would leave me 20 on. Okay, yeah, it should be A minus 1. A little typo there. So that should be A minus 1. Sorry about that. Now the between case. So between 10 and 20. Well, if we have that's going to be 10 is less than or equal to x is less than or equal to 20. So this is going to be our A, and this is going to be our B. That's from this notation here. So that says we're going to set that up as Poisson distribution, our mean, which was 10, and then B was 20, minus Poisson distribution, mean, which is 10, and A minus 1, and A was 10, so you got 10 minus 1. Now, what made me have to think of the setup on that previous one is if I think what this includes x value wise. goes up to 20. So this is 0, 1, all the way up to 20 in terms of possibilities. Now this one is 10 minus 1, which is 9. So we got 0 through 9. Okay, now if I think of this as listing all the possibilities, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. If I subtract off 0 through 9 in terms of possibilities, you can see that leaves me 10 through 20. And that's what I had to think through in that previous problem. It used to be when you worked these problems, you had to actually think this through yourself like this. But then I decided I'd come up with this table since students struggle with it so much. So they could just use your table to plug in your values and come up with the answers. Well, that's the last item I was going to cover today, so I'm going to stop the recording, and then I'll answer any questions you have.